everyone. I'm Yuki. I'm a PhD student and a full-time researcher at Japanese cloud computing provider. And actually, this is my first time attending Cubicle North America and WasmCon. Thank you for giving the opportunity. So today, I'm going to talk about self-hosted Wasm runtime for runtime neutral extensions and capabilities, a part of my PhD research. As you might know, portability is one of the key concepts of Wasm, which is achieved by two natures of Wasm bytecode. The first is language independent. Wasm bytecode is independent of specific languages, allowing programs written in any language to be compiled to Wasm bytecode. The second is hardware and platform independent. Wasm runtimes abstract hardware and platform, enabling Wasm bytecode to run on any hardware and operating systems. These nature enable write once and run anywhere. There are currently over 100 unique Wasm runtime implementations. They differ in execution models like interpreters, JIT or AOT, target platform, and workloads. For example, Wasm time achieve high-performance Wasm bytecode execution with JIT compilation, and Wasm Edge offer rich extension for AI workloads. But this runtime diversity imposes limitation on Wasm's portability. Each runtime implements its own unique capabilities. For example, Wasm Edge has capabilities like statistics and resource limitation, which are needed to run application in production, but not all implemented by all runtimes. Moreover, while Wasm has a standardized variety of features, their support status different across runtimes. As a result, there are limitations on the available runtime and the features usable in Wasm bytecode. So, how can we use or implement the runtime neutrality? My approach is a self-hosted runtime for runtime neutral extensions. It's a minimal Wasm runtime compiled to Wasm itself. In this architecture, we can execute Wasm bytecode via self-hosted Wasm runtime. It can be used as a compatibility layer for host Wasm runtimes, implementing only extension for the self-hosted runtime, allowing running them without modifying diverse host runtimes. I implemented a proof of concept self-hosted runtime called Chihuahua. So, what are the use cases of runtime extension using self-hosted runtimes? The first case is a cross-runtime checkpoint and restore. Checkpoint and restore is a technique for saving an application execution state and resuming the application from that point using the dumped state file. It needs to modify runtime performance optimization techniques and implementation because it refers to and modifies the stack, program counter, and linear memory in the runtime. Self-hosted runtime-based checkpoint and restore does not need to consider runtime differences because it uses state in the self-hosted runtime. The second use case is tracing and instrumentation. Tracing and instrumentation support understanding internal state during Wasm bytecode execution. They help with bug detection, visualizing, processing, flows, and profiling. Self-hosted runtime-based instrumentation enables precise tracing, including the execution state within the boolean instruction. The tracing platform using a self-hosted runtime can achieve this without modifying any runtime. The final use case is execution Wasm features not supported by the host runtime. In this use case, the self-hosted runtime executed as a compatibility layer. We implement the interface and functions of the unsupported features. Then by comparing the self-hosted runtime into Wasm bytecode executable by the host runtime, and it can be executed compatibly within the scope supported by the host runtime features. For example, let's think about WASI P2. The self-hosted runtime supports WASI P2 and it compiles to WASI P1. Executing it on a host runtime that only supports WASI P1 enable WASI P2 bytecode to run compatibly. However, duplicate execution of the host runtime and self-hosted runtime cause performance degradation. Two factors are causing this. The first is increased Wasm bytecode instruction executed in the host runtime. As shown in the figure, a single Wasm bytecode instruction in an application is handled by a self-hosted runtime handler compiled into Wasm bytecode, causing a single instruction to transform into multiple instructions. The second factor is duplication of computationally expensive operations. The sandbox and WASI implementation are not only frequently executed, but also known to be highly resource-intensive, consuming significant host resources. To tackle this issue, I implemented two performance optimization techniques in Chihuahua. The first approach is instruction merging. When passing bytecode before execution, this approach identifies dependencies between instructions and merge multiple instructions as shown in the illustration. An argument fetched via the stack converted to immediate value, and local or global variable update via the stack and converted to direct updates. This greatly reduced the number of stack push and pop operations. The second approach is a pass-through WASI implementation. This calls the WASI implementation in the host runtime and redirects WASI function processing to the host runtime. This means the WASI implementation in the self-hosted runtime does nothing except redirect to the host runtime. I evaluated the performance of Chihuahua. First, I compared its performance with Wizard and existing self-hostable runtime using primitive computational benchmarks. Chihuahua achieved about 1.4 times better performance than existing self-hostable runtime. This improvement is due to optimization techniques. Next, I compared the SQLite benchmark scores between running directly with Wasm time and running with Chihuahua on Wasm time. The experiment results showed that the self-hosted runtime suffered a significant performance degradation. This is primarily due to substantial overhead still incurred by the duplicate runtime execution. And to conclude my presentation, self-hosted runtime helps implementing or testing feature and runtime capabilities. It can run on any runtimes without modifying them. However, a self-hosted runtime causes significant performance overhead. So performance optimization techniques are essential. My future goal is to achieve performance equivalent to execution in the existing interpreter runtimes. I'm currently exploring further optimization techniques for the self-hosted runtime as a PhD research. Thank you for your attention.
Hold on. He's going to bump beep, but there it goes. There it goes.
Did you do any SIMD? Did you get to any SIMD instructions?
SIMD?
Actually, my implementation, it's not supported. Maybe it's feature lock.
Fair enough. Other questions? Over here.
I might have missed it. Where do these optimizations happen? Like, what's What compiler is doing this?
Oh,
Like, is it during JIT time? Is it AOT compilation that's doing these optimizations that you showed?
yeah. So actually, my POC implementation considered that, and now my implementation, my prototype parsing bytecode in the self-hosted runtime. So host runtime, it means my approach can't apply the host runtime optimization like JIT compilation in Wasm time. So anyway, it's feature like so.
Other questions? You can pursue the question after the presentation as well. Thank you very much.
Thank you.